In machine learning, the learning part is backpropagation. This is the part where you train the model to learn new things, and you do this through backpropagation. The idea is that we have a whole series of matrices, a whole bunch of matrices. These matrices are in series, and when we want to train the model, the first thing we have to do is ask it a question, and then we see how far off it was from the answer. Then we take the delta from the answer. The delta is actually calculated through backpropagation. That's the part of saying how far off is the model. The model, when you get started, is going to be wildly inaccurate. It's going to be essentially random. And then you want to be able to detect how far off it is from the intended target. Say we have a word, and the word is like hello, and then we want to say if the word is positive or negative, like in tone or something, right? And we know that ahead of time. We want to train the model to learn this. So we'll pass the hello into a tokenizer, which turns it into an integer, and the integer might have an embedding, turning it into a series of floating point numbers. Now that's your first matrice. That's your input matrice, right? That part happens here at the top. So you still have to do this part. You still have to give it the prediction part first. So we do the feed forward aspect, and then we move forward. Here is the definition of the forward function. You can see it's actually pretty straightforward. We grab the inputs, and then we do a matrix multiplication right here with the layer, right? So we've got the layer, which is the weights. It's called the weights here, but it's really just a matrix. And then we do multiplication with the input. So we did matrix multiplication here in this phase, which gives us an output. And then we just do this in a series for all the layers in the model until we get our final output target. So it kind of looks like this. This is a visual diagram that shows us here what that looks like. So we have our inputs here, which are going to be our words, right, or a sentence that gets thrown into the first layer of the matrix, right? This is the matrix multiplication. Then we do another matrix multiplication, and another one, and another one. And then we get our output answer. And this is what the model thinks is correct, right? It thinks, oh, this is a positive word. Hello is a positive word. In that case, it would be correct. But how positive is it, right? It might think that it's a little bit positive, but the word is actually pretty positive. So we want to detect how far off it is from our thought about it, right? We think that should be more of a positive word. So what we do is we take the output and we just go backwards, right? We look backwards, and then we calculate the delta, because we know what the actual answer is, right? We know that it's a positive word, and the AI model also thinks it's positive, but not as positive as we think it should be. So we will then calculate essentially the difference, right? How far is it off? And that looks the same from programmatically. It looks basically the same. We just go backwards, right? So we have this invert here, and invert the array, and it just goes backwards through the matrix. And then the gradient is the output, which brings us all the way back up to the input layer, which is the original layer. And then we are able to determine essentially corrections, right? Every layer will need to be corrected ever so slightly in order for us to then achieve our target output. This is called the optimization step. And we take the layer matrices, right, the weights, and then we slightly adjust it. We subtract just a little bit. We take the delta, which is called the gradient, how far off that one layer is from its intended target. And then we shrink it a bit with the learning rate, right? We might want, if it was 100%, then the model would immediately learn that the word hello is exactly as positive as we wanted it to be. Oh, but that's a problem. We can't do that, because then if we try to teach it another word, then it will forget hello. We don't want it to forget hello. We want it to remember. So we have to slowly iterate with a whole bunch of words, a whole bunch of different instructions. And then over time, it will be able to learn all the words. But it's really simple. Look, this is the training part. We're just slightly modifying the matrices just a little bit by what we've learned through backpropagation. That backpropagation just tells us the delta, how far off that number is. Maybe it's off by 2, right? It's off by 2. So then we will make a correction by 0.2, say if we wanted the 10% learning rate. So we're talking about backpropagation with machine learning. There is another detail that we have to be familiar with, and is the activation function. The activation function is a function that essentially is a normalization, right? So when you're doing a matrix multiplication across all the different floating point numbers in the matrix, your output layer could start growing and growing and growing very, very big very quickly. We don't want that, because that causes like hot spots, right? Spikes. and things can get stuck there. We need nice smooth gradients, and one way to do that is through activation functions which normalize. Common activation functions are like tanh and sigmoid. ReLU is a popular one because of its efficiency. During forward propagation, we have this activation that occurs here, which happens after the matrix has been multiplied with the inputs. Really simple and straightforward. So then, for example, this could be, the activator could be tanh, right? So we'll throw that around that, and what that'll do is the numbers, instead of growing to like 100,000 million billion, you'll shrink them into a unified space of a number between -1 and +1, and it will always stay within that zone, which makes it a lot easier forward propagation, larger number of layers. And it's also used in the back propagation, but in reverse through the derivative, which is kind of like the opposite, the activation function, right? So we need to undo the tangent or undo the sigmoid. So after we've multiplied so through this training process, as we're going backward, we do the matrix multiplication backward again, this time with the derivative, and we apply the derivative to the input and the weights like this. So it's a simple one line, essentially a simple one-liner, and it's really straightforward. So we've done the back propagation, and then we need to apply the derivative to it as well. 2 lines, nice and easy. Back propagation also has to have this, and this part of going backwards, right? We have to do all the backwards because we need to detect the deltas. What's different? What's changed in the model? What, like the target output? We see it. It's right there. The model came in under or below, but we needed to get a little closer to our desired target output. We determine the delta and how far it was off for each of the layers in the model, and then we can slowly apply the optimization. We apply the optimization based on the learning rate.